All right, everyone. So I would like to welcome you all to EPSP Connect. My name is Scott Feehan. I'm a PhD candidate at the University of Nevada, Reno. And on behalf of the entire EPSP Connect team, I just wanted to thank you for joining. Before we get into our talk today, I would just like to announce our fall lineup is set. And so we will have a couple events in the upcoming months, starting with Robert Mahone on September 22nd. On October 13th, we have a science talk from Jocelyn West. And on November 17th, we have another talk from Kristen Sweeney. So we hope to see you then. And now for our talk today, it is my pleasure to introduce Dr. Marisa Palucis. Marisa started her academic journey at the University of South Carolina, where she received her bachelor's in chemical engineering. And then she moved on to UC Berkeley, where she received her PhD in Earth and Planetary Science. And this was followed by a postdoc at Caltech. And now at her current position is as an assistant professor in the Department of Earth Sciences at Dartmouth College. And so without further ado, I'd like to pass it over to you, Marisa.
Thank you. Okay, can you guys see that? Okay, I'm gonna shut everyone's faces. Okay. So thank you all for having me here today to be part of the EPSP Connect series. Definitely an honor. And thank you all for attending, those of you that came. So today I'm going to be talking about some work that I did with two of my now former master's students. And this is work that basically is building on work that I did when I was on the Mars Science Laboratory MSL team in 2014 and 2016. And so basically our group was interested in thinking about if we can provide additional insight on the paleoclimate and paleohydrology of the Gale Crater region. And for those of you that don't know, Gale Crater is a large crater on Mars. That's the home of the Curiosity rover that landed in August of 2012.
No, that's correct. We did have a discussion on.
Sorry, someone's looking.
Sorry.
So this is really a group effort. So this was work that was done in collaboration with Dr. Francis Rivera Hernandez, who is now an assistant professor at Georgia Tech. My master's student, Audrey Putnam, who's now a graduate student at Rice with Kirsten Seebach. My master's student, Tori Roseborough, who's now a researcher at ASU. As well as my undergrad, Melanie Canine, who's now a graduate student at Caltech. And this work was supported by two different NASA grants, as well as funding from Dartmouth. Okay, so I always love showing this photo in talks, just because I love thinking about when you look at Mars and Earth today from space, how different they appear. So Mars is about half the radius of Earth. It takes about 670 days for Mars to orbit the sun, and its gravity is about 1/3 of ours. The temperature, the mean temperature on the surface of Mars is about -81 degrees Fahrenheit. And so basically Mars is not conducive to liquid water. So if you put water on the surface, it will either sublimate or freeze, but liquid water is not happy on modern day Mars. Now, if you kind of zoom in and look at sort of Mars from a topographic perspective, it has a really interesting sort of dichotomy. And so you can see here in this sort of global topographic map that the southern portion of Mars is topographically higher. So this is indicated by the warmer colors than the northern lowlands. So this has led to a lot of speculation about whether or not Mars once hosted a ocean, because if you have water that were to melt or rain on the surface, it would potentially drain and pool into the northern lowlands. I also really like this image because it shows all of the different missions that are either currently on Mars or have been on Mars, which just shows sort of the excitement that we have had as a community for understanding this place. And if we zoom in even closer, so if we start to look at some of the surface features on the planet, I think this is where a lot of us get really excited because there's all of these features that indicate that liquid water must have been abundant at some point in Mars's history. And so you have these branch valley networks, you have beautiful deltaic deposits. So this is the Eberswalde Delta. It's very similar in form to the Jezero Delta that the Perseverance rover is now studying. And so, this has really led to, I guess, in my opinion, some of the key questions that we have had in Mars research. And so I would say one of the big ones is that all of us that study this planet is, did Mars host environments in the past that were habitable? And if so, what was the duration and extent and timing of these habitable environments, or maybe more specifically of water on Mars? And then also, how is Mars's climate record being preserved in the geologic record? So in today's talk, try not to take too long, I'm going to briefly go over the history of Mars for those of you that don't think about it all the time. I'm going to talk a little bit about the extent and timing of lakes in Gale Crater. Then I'm going to move on to thinking about sort of regional evidence for other large lakes in the area. And then using sort of this history of lakes, can we get at sort of the water sources to Gale Crater as well as these other surrounding craters? So were these craters fed by groundwater exclusively, by surface water, things like that. Okay, so one of the things I also love about Mars is it only has 4 main geologic periods. So unlike my friends in Earth history, who I feel like have to learn like 200 different time periods, I only have to know about 4, which is great for me. And it's divided up into sort of the pre-Noachian, which is about 4.6 billion years ago, to about 4.1. Then about 4.1 to 3.7 is what we call the Noachian. And then we transition around at 3.7 into the Hesperian. And then at about 3 billion years ago, we kind of enter into sort of our more modern day climate for Mars, which, as I said, is very cold and dry. And so it is thought that early on in Mars's history, there was a magnetic field that would have lasted, about up until this Noachian Hesperian boundary. Early Mars, as you might expect, was subject to a lot of bombardment by craters. And this is when we think a lot of the large impact basins were formed. So some of the large depressions that you see on Mars, like Hellas, Argyre, and Isidis, occurred early on. There's also a lot of volcanism. So around sort of this pre-Noachian into the Noachian is when we believe the Tharsis Bulge started to form. So that's that sort of big volcanic edifice that's on Mars. And then we've had sort of what we think sporadic volcanism ever since. So even into sort of more, modern day times. The surface chemistry of Mars is really interesting. So we think a lot of the magnesium and iron clays formed early on. Many of them maybe in the pre-Noachian and into the Noachian. And then around sort of the Noachian Hesperian, that started to transition. And so we started to see the formation of more aluminum clays, but also the beginning of sort of these more evaporitic deposits and sulfates. And this sort of continued through the Hesperian. So this is now where we think we were starting to get sort of going from a wetter climate. Now it's starting to dry. And then we get these dry ferric oxides forming in the Amazonian. Something that I think as geomorphologists, we're all really interested in is the surface hydrogeology. So basically thinking about the history of water. So at this Noachian Hesperian transition is where a lot of the valley networks that, many of you may have seen likely formed. But then also sort of the sporadic formation of younger fluvial features. And so something that's really, really interesting is a lot of us who are thinking about sort of alluvial fan formation, so sedimentary deposits that don't form in water. Some of those might be as young as 1 billion years old, which, yes, is very young to us. And so that really then calls for appreciable amounts of water, even in the Amazonian times. This Nowakian Hesperian transition, which I'm guessing you could see is kind of an interesting time, is also when we think a lot of the outflow channels formed. And so this has sort of led to a conceptual model that basically early on in Mars's history, it was potentially dry but warm. And then we had sort of this climate optimum at around 3.7 GA, where we had warm and wet conditions, potentially with high runoff. And then as we sort of moved into the Hesperian and Amazonian, things became colder and drier, less groundwater, and sort of, we now have the Mars that we know and love today. And this sort of assumes that there had to have been some continuously warm environment maintained by greenhouse gases. Now there is sort of an end member hypothesis, and this is based a lot on people who do numerical modeling and global climate modeling, who are trying to understand climate from maybe less of a surface feature perspective and more from a modeling perspective. And it's really, really hard in the numerical models to get a sort of warm, wet Mars. And so this has led to sort of an icy highlands hypothesis. And so that basically Mars has always been relatively cold and dry, more glacial in nature, and that you've had periods that were transiently warm. And so during these periods, either from volcanism or from impacts, you were able to warm the surface, and that would be when you create liquid water that can create some of the surface features that we see. And I would say that this is still a very active debate about which climate prevailed and for how long. Okay, so sort of with that overview, I'm going to move on to thinking about, or talking a little bit about Gale Crater, since that's sort of the focus, or at least the Gale Crater region is the focus of today's talk. So I first want to say that the interest in Gale is because we believe, or we have a lot of evidence that it hosted paleo lakes. And so Gale is very special to us. And, we do have a rover, the Curiosity rover, that's been there for a while now exploring Gale. We also have Perseverance, which is in Jezero Crater, also looking at another crater lake. But paleo lakes have been mapped across Mars. So it's not that these are, the two only lakes that we know of. And so this is a really nice map from Tim Gouge and others, looking at these features. And why we're so interested in paleo lakes is just because they really are important astrobiological targets. So we're humans, we're interested, are we alone? Mars has, for decades now been a place that we think about, could life have evolved, and could have evolved right next door to us. And so I pulled this from a paper from Tanya Bozak and John Grotzinger and others that just came out, a review paper, looking at sort of the astrobiological importance of lakes, and what, they hope to find in, looking at some of the sediments in Jezero, or what we might see in Gale Crater. And so you can imagine if you have an active hydrologic cycle and you have a depression or a crater, you're going to get sediment and water and clays and all of these carbonates, all of these interesting sort of building blocks for life that are going to accumulate within these basins, and that these materials might possibly can be preserved. And they point in this paper to some of our oldest things like stromatolites on Earth, so 3 billion year old stromatolites, or some of these laminae that got preserved in a conglomerate that are Archean in age. And so lakes are just a really, great place for us to study. And, that's evidenced by the fact that we've sent 2 rover missions to 2 different lakes on Mars. Okay, so focusing in on Gale. So this, as I said, is the home of the Curiosity rover that landed in 2012. This is a very, I admit, garish topographic map that I made in like 2014. But I really like it. I like it because it shows that the Gale impact occurred right on the crustal dichotomy. And so you could see here where this is higher topography up by Herschel and Lassowitz, and that this topographic gradient here is about 2%. So most of the water, or if you had ice and water that's draining, is going to drain potentially into Gale and also into these northern lowlands. One of the really fascinating things about Gale Crater was the fact that it had a 5-kilometer high sedimentary mound, which you could see here. Looks kind of like a little crown in the center of the crater. And it actually is 2 kilometers higher than the northern rim, which has been likely eroded away since Gale formed. And this is the Curiosity rover landed on the northern portion of Gale, so where that yellow star is. Now, I'm not going to go into great detail about this, about all of the discoveries that have been made by Curiosity. I feel like there's way better people to go into all of the cool stuff that has been found since the landing. But, you know, kind of earlier on in the mission, or when I was still active on the mission, the Curiosity rover landed near an alluvial fan and landed near sort of beautiful conglomerates. And then as it traversed from the sort of northern rim towards the central mound, it encountered sandstones and then mudstones. And so sort of this, not just the sedimentology, but the geomorphology, the mineralogy, you know, geochemistry, all of that taken together really sort of suggested to the MSL team that we were driving through an ancient lake deposit. And so the sort of conceptual model here is that you have the northern crater rim, which has sort of an alcove that would collect snow, and this is also where you would source sediment. That sediment would be transported down, deposited into a fan or fan delta system, and then eventually into a crater lake. Now, one of my roles on the mission, and this is work that I did, you know, with Bill Dietrich and others, is basically thinking about what if we step back from the rover, from the landing site of the rover, and sort of think about the more regional context as well. So, you know, we had discovered evidence of this ancient lake environment, which obviously this, you know, first a habitable environment. But was there other evidence that could help constrain sort of the hydrogeomorphic history of Gale Crater? And so we spent a lot of time basically looking still within Gale. It's a huge crater, it's 150 kilometers in diameter, and using orbital imagery, which is how most of Mars has been studied, is using remote sensing and techniques and orbital imagery. We mapped out a series of delta deposits. So these are all colored in sort of a light blue, as well as fan deposits. And again, an alluvial fan is basically a deposit that's forming not into standing water. And so we have several larger fan deposits, including the Peace Vallis fan, which is at the landing site, as well as smaller fans that sort of ring the sort of are along the wall of the crater. We also map sort of these large valley networks like Farra Vallis and some of these that are feeding delta deposits. And this, we call this the entrance canyon. It's now Geddes Vallis. But from our mapping, we think that there may have been up to at least 3 stable lake stands within Gale Crater. And these were quite large lakes. So this orange lake would have been about 700 meters deep, and these smaller lakes would have been about 300 to 400 meters deep. But this sort of, while it tells us that, oh, and I should point out before I move on, that the lake discovered by Curiosity, we think that that formed before the large central mound. So there's sort of the lake deposits that we observe from the rover early on in the mission, and we believe that was an early lake. Then you have sort of the deposition and formation of this mound, whose mechanisms are still being debated. And then post mound formation, we think we have these 3 large lakes, if not more. And so this really tells us that Gale was a very dynamic place, and that there was a very active, you know, hydrologic cycle, and that there were periods of, you know, lake activity as well as lake level decline. But we really wanted to know, you know, it kind of feels like, or it felt like to me when we were on the mission, Gale was the most important place, and it is. But at the same time, these are large lakes. And so it makes you think, well, what's happening outside of Gale? And can we use sort of a more regional understanding to get at maybe better understanding the water sources to Gale, how long there was water in Gale, where, you know, was it mostly supplied by groundwater, surface water, and can that tell us anything about the climate? And whether, you know, did life have time to evolve in this crater or not? So I will try to go through this quickly. For those of you that aren't planetary scientists, when we want to get at time on Mars, for the most part, we use crater counting. And so in terms of thinking about the age of an individual crater, oftentimes we use the ejecta blanket. So the idea is you have an impact that happens and it spews out all of its ejecta and creates these ejecta blankets. And that, you know, at time 0, there's going to be no craters on that ejecta blanket. But then over time, as craters continue to bombard Mars, the ejecta blanket's going to have more and more and more craters on it. And the more craters it has, the older likely that ejecta blanket is. There's all sorts of caveats to that, obviously, but that's the basic premise. And then you can count, you can bin your data, so you can look at the diameter, the number, basically count the number of craters at a given diameter and put it on this isochron plot. And these plots then have been calibrated to lunar data. So on the moon, we also can do crater counting, but we also have actual ages that we can tie to those counts because the astronauts were really nice and brought us back rocks that we could date. And so doing this technique, it's been found that Gale is likely, the impact occurred probably around 3.6 billion years ago. So sort of right at or before that, or right near that Noachian to Hesperian sort of climate optimum that I talked about earlier. Now, getting at the timing of the actual lakes is really hard. If you want to read maybe the nerdiest crater counting paper ever, I can send it to you. And this was something I worked on with Bill and others for a while. But the basic gist of the story is that when you have a really small feature, like some of these deltas, it's really hard to trust the crater counting. And so another way to sort of get at that is basically to count the floor of the crater, to count all the craters that are on the floor of Gale, make the assumption that that basically during the time of lakes, it was sort of like a resurfacing event. And so after the lakes disappeared, you were starting at time 0, and that the craters accumulated since would tell you when the lakes last existed. So with those sort of caveats and assumptions, it would suggest that the time of lakes in Gale occurred between about 3.5 and 3.3 billion years ago. And so these are counts that we did here on the left, and then more recent work by John Grant and Sarah, or Sharon Wilson, I'm so sorry, Sharon, also confirm about 3.3 billion years. Now, the fan deposits suffer from the same fate as the delta deposits. They're tiny, 100 square kilometers or so in size. So it's really hard to also do crater counting. Sharon and John did basically a sort of lumped method where they basically mapped the craters on all of the fan surfaces and added up sort of all of the surface area to try and get a larger area. And so in doing that, the fans would be about 1 billion years old. So the fans could have formed as late as about 1 billion years ago, though, they could be older. It's just really hard to tell on these really small features. Okay, so we know that Gale was a dynamic place, that lakes existed likely during sort of that Noachian Hesperian climate optimum. And so we wanted to look, or my group wanted to look at sort of thinking about, well, is there evidence for other large lakes or hydrogeomorphic events in the region? And so this ended up being the master's for my student, Audrey Putnam, who, as I said, is now a PhD student at Rice with Kirsten Seebach. And she did a really amazing job doing this work all through COVID. So wrote her dissertation, this paper, everything at the start of the pandemic. So, major kudos to her for doing that. And so basically what Audrey did was went just a little bit east of Gale and went to this crater named Gale Crater, which you can see sort of here on the right in this high resolution imagery. And so Audrey used a variety of different methods to try and get at sort of the hydrogeomorphic history of this crater. So traditional sort of geomorphic mapping using HiRISE. So HiRISE data on Mars is really nice. It's 25 centimeter per pixel, so really high resolution. CTX imagery is also great. It's 5 to 6 meters per pixel. She also used some thermal imagery. She did paleoflow and mass balance analysis using topographic data that she derived from the CTX images. She looked at the mineralogy of the crater deposits using CRISM, which is a hyperspectral data set. She did some crater counting of the Gale Crater ejecta, so just like it was done for Gale. And then also worked with Dr. David Horvath, who's at PSI, utilizing a surface water groundwater flow model. All right, so the geomorphic mapping was based on a combination of both using the topography, so the topographic data, as well as using the imagery or visual data sets. She mapped 18 major geomorphic units within Gale Crater. And I'm not going to go into all of the details of all of them, but she did do a ton of work, and there's a lot of interesting kind of smaller stories within her mapping. One of the things that was really interesting was she found what we think is a smaller delta deposit on the eastern floor of this crater, along with several channels that would have potentially been as the crater just started to fill up. So basically evidence of a very early lake. What I'm going to focus on more is this sort of bigger, what we infer to be a deltaic deposit on the western, on sort of the southwestern rim of the crater. So when we look at this particular deposit, we see that sort of morphologically it's similar to what we might think would be sort of a deltaic deposit. So it's arcuate contours. It steepens into multiple fronts. This deposit itself is about 10 kilometers long and about 50 square kilometers in sort of aerial extent. The slope is pretty constant at about 10% for the entire delta. One of the things that we like to do is a mass balance. And the reason for this is just that, for the data that we have, one indicator, one of the nice things about deltas, or one of the things that, we try and do with the deltas, or these Gilbert deltas, is use sort of the steeper fronts to understand where the paleo water level would have been. But the idea is that we want to also, a lot of these deposits are subject to erosion over time. And so by doing a mass balance, it gives us some idea of how well preserved these features might be. And so Audrey did spend a lot of time trying to reconstruct sort of what the topography of the crater underneath the deposit would look like to do this mass balance. And so then basically she estimated the amount of material removed from this canyon to be about 6 cubic kilometers, and then the amount of material that is now deposited in the delta, which was about 5 cubic kilometers. So not all of the material has been preserved, so we acknowledge that. So there is going to be some error potentially in when we try and make estimates about sort of the maximum extent of the lake within this crater. And obviously we're also making an assumption that this is sort of a volume balance. We're basically saying that the volume of material as it's being removed from the canyon is similar to, or that there's not a major porosity change or things like that over time. So given those caveats, we do think that this delta is fairly well preserved, though some of that material has likely been eroded away or was transported further as fine grain material. Now, Audrey, unlike me, I'm a horrible mineralogist, but she was really, really interested in looking at the mineralogy of Gale as well. And so she spent a lot of time working with Abby Freeman during a summer internship, learning how to work with PRISM data. And so she wanted to look at sort of the mineralogy of the crater. And so she spent a lot of time looking at this particular deposit, and confirmed earlier findings from Haber and others, as well as found some, new sort of signatures of hydrated silica. And so the idea is basically that if you have hydrated silica or hydrated opaline silica, if it sits in water for really long periods of time, it'll eventually be converted to quartz. And so it sort of places an upper or a bounds on how long that these sediments would have interacted with water. So the idea here is that because we see these in this hydrated silica sort of detections in the front of these deltas, that the sediment would have interacted with the water for less than about 10 to the 6 years. Now, in terms of looking at this deposit, the Guru deposit is really, I don't want to say, it's kind of odd looking. There's a couple of deltas like this across Mars, but it does look very similar to delta deposits that have been created in experiments where you have a continuously aggrading, backstepping environment. So when you have basically like a constantly rising lake level. And so this is an example from a experimental delta from Mudo and Steele. And this is sort of kind of looking at kind of the front. So you're looking sort of at the delta deposit, and you can see it has a similar morphology. And so this suggests to us that perhaps this delta is recording sort of a constantly rising lake level through time. Now, again, within the caveat of our mass balance, if you look at sort of the highest front on the delta, this would suggest that at its maximum extent, Guru hosted a 0.7 kilometer deep lake that would have been 570 square kilometers in area. And this image is vertically exaggerated, just so you can get a sense of sort of the lake. And like many deposits on Mars, this is something that's also, I think, really, really interesting is when you look at a lot of these delta deposits, is that they don't tend to have a lot of post-depositional incision, suggesting that the surface water would have shut off rapidly. So you get shut off of surface water and then probably evaporation of the lake itself. There are these, kind of, I think, kind of strange gullies that are pretty wide. They're about 20 kilometers deep. And in high rise, you can see sort of the layering. And we tried to make dip measurements on this, but within the error of the CTX, it really didn't tell us much because obviously you really want to see, if you want to show that there's a delta, you want to see those nice sort of top sets and cliniforms and things like that. Okay, so how long did the Guru Lake persist for? So this is one of the things that we try and estimate is, and again, this is important when you're thinking about habitability. So if a lake exists for millions of years, that might be a good sign in terms of concentrating organic material or providing sort of breeding ground for microbial life. If it, lasts for 1,000 years, then, it's less likely to potentially be a sort of strong astrobiological target. And so basically we looked at sort of if we assume that the lake was filling up from the canyon alone, we can estimate the discharge. So using the continuity equation, so the average flow velocity times the width times the height. So Audrey kind of estimated what we think sort of the channels, the size of the channels within that canyon would have been like. And then we use this variable power resistance equation from Ferguson to estimate our flow velocity. So this gives us basically like a friction factor, and then we can estimate our average flow velocity from that. And then to get at delta formation timescale, we can take the delta volume divided by our sediment flux, which in that case, we have to assume sort of a rock to water ratio. And we use the methods in Mathieu's latest paper to get at delta formation timescales, and then also to get at how long it would take the lake. So we know we have an estimate of the lake volume, and we know the discharge coming into the lake. We estimate the volume or the discharge coming into the lake. And so basically we do that. We get the bankful discharge estimates are about 200 to 600 cubic meters per second, which is not crazy for a lot of these similar types of estimates that are made, for Jezero or Gale or places like that. That would have taken 10 to the 2 and 10 to the 4 years minimum to fill this lake. And then it may have persisted for about 10 to the 5th years. Okay, and so in thinking a little bit about timing, because again, we're trying to tie this to Gale. We're trying to think, is what's happening in Guru it all being reflected in what's happening in Gale Crater? And if they are, then does that say something about maybe a shared water source? And so to get at when we think Guru impacted, Audrey did a similar, as I said, similar to what we did for Gale, and we looked at doing crater counting of the ejecta. And so we think that Guru impacted about 3.5 billion years ago. You can see here, we see this for Gale too, that these were sort of likely pre-existing, valley networks. So these would have been active before the Guru impact. Gale, we see similar features where the Gale impact sort of covered these pre-existing network systems. And I just want to remind you guys that, that if this logic is at all correct and the crater counting is at all correct, that we think that Gale lakes would have formed between 3.5 and 3.3 billion years ago based on our crater counting. Now, another observation that Audrey made was that Guru really lacked any detections of sulfates or salts, whereas Gale is abundant in them, and so especially in its mound. And so one hypothesis is that potentially, Guru, the lake filling Guru or the water source that was filling Guru would have been post-mound deposition. So when we put this all together, the idea is basically that, pre 3.6 to 3.8 billion years ago, we had these regional valley networks that were active. Whether they were active when Gale impacted, we don't know, but Gale did impact probably around 3.6. And that early on in Gale's history, we would have had potentially that lake that the Curiosity rover discovered. And we also would have started depositing the sediments that would have formed Mount Sharp. Around about 3.5, we would have the Guru impact. And so we think shortly after Guru impacted, it started to fill with water. And this is also would have been around the time that Mount Sharp was sort of eroding back and forming its later stage lakes. And so we think that potentially both Guru and Gale would have been filling up sort of at the same time. And with Guru, this early shallow lake, and then transitioning, it would keep filling up into this later deeper lake that formed that larger deltaic deposit that's coming in from the western crater rim. And then that we think that if the mapping with Gale, the floor of Gale is correct, is that maybe Gale Crater would have not have been significantly modified after about 3.3 GA, so that potentially both of these lake systems would have shut down. Okay, so what about the sources of water to Gale and the surrounding craters? So we've talked a little bit about this dynamic lake history. It seems that other lakes in the region, at least where we've done this detailed mapping, also have interesting sort of lake dynamics. Large lakes were, common not just in Gale, but maybe in other nearby craters, potentially at the same time. So how are they all connected? And so one of the things that we know, this is both, I'm just showing Guru because Audrey had a really nice image in her paper from it, but Gale is very similar, is that we have these amphitheater headed sort of canyons that are basically incising into the crater rims, both kind of coming from sort of the western side, the southwestern side of the crater. But oftentimes that upstream of these canyons, we see, unincised ejecta blankets. So there's not a lot of evidence of really concentrated runoffs. We don't see sort of, well-developed stream networks leading into this. Which also could be a preservation issue, of course, considering we're talking about billions of years old. And so this does suggest potentially that groundwater could be an important mechanism in maybe forming some of these canyons, or at least supplying water to these craters. And so this is something that Tori Roseboro took on for her master's project. And so basically, Tori and I worked with Dr. Horvath to think about whether or not Gale Crater was connected to a more regionally extensive groundwater system or not. So one of the things, and I don't think I pointed this out earlier, but one of the things that we noticed when, I was working with Bill during my PhD was that there's these smaller sort of gully networks, and they all seem to terminate at these different lake levels. And so we decided to we actually noticed this occurring in, Tori was mapping for actually a different purpose. She was mapping gully networks in other craters nearby. I believe this is in Herschel. And we noticed that the gully networks also seem to terminate at a common elevation across the crater. And so we thought, well, maybe we can use these as sort of indicators of past lake levels. So kind of using Gale as our example, because in Gale, we also had deltas, multiple delta features, and canyon deposits, things like that to sort of constrain the lakes. We didn't think too much about the gully networks, just the fact that it was interesting. They seemed to terminate where we saw these lake levels occurring. And so what Tori did was she basically mapped these smaller gully network features across a number of craters upstream of Gale. And then she would sort of map, for each gully that she would map, she would basically extract using MOLA or HRSC data to get at the elevation. And in that would find sort of that there was a broadly consistent termination elevation of these features. And in some cases, like in Gale, we see multiple, we see sort of a bimodal distribution, which is potentially due to the fact that we had in Gale multiple lake levels at different times. And so Tori did a really exhausting mapping effort across the Gale Crater region. And so all of these kind of blue lines are previously identified regional valley networks that were mapped by others. The darker blue are craters that people that like Tim Gouge and Caleb Fassett had previously identified as paleo lakes. And then Tori did mapping in all of these other basins and craters. And basically the white lines are sort of our inferred lake level contours. And so she found that there was maybe 22 possible paleo lakes that were upslope of Gale Crater. And so this is where we turn to Dave Horvath, because he had done modeling and published a paper in like 2017, modeling just Gale Crater, the lakes in Gale Crater using our mapping to sort of constrain the lake level. And so we asked him, hey, can we like extend this out to the entire region to see if there's a climate condition that would match all of these different lake levels that we're seeing, that might suggest, if they all sort of matched up, that there is a similar climate that was, or groundwater system that was sort of feeding all of these lakes at the same time. And so basically, Dave was awesome and said yes, even in the middle of a pandemic, right after having his first child, that he would help us with this modeling project. And so we looked at a number of different aridity indices to do this. We looked at basically climates that were subhumid up to arid. And this index is basically a ratio of the evaporation potential to precipitation. We did make certain assumptions. We said that the annual precipitation had to have been about 160 millimeters per year. This was actually a constraint that he used based on our estimates from Gale Crater. The mean annual temperature had to be greater than 0 degrees C, that there was equal partitioning to recharge and runoff, and that there was a laterally homogeneous aquifer, and that porosity decreased with depth. So obviously, being on Mars, we don't have cores, we don't have all the things on Earth to sort of really constrain these, some of these parameters. So we sort of, basically did the best we could. And I'm just showing sort of an up close image of sort of the model output showing one of our lake levels in Gale that best matched. So this is the Pancake Lake. And you can see that this, where it's darker or where it's gray, this is where water would pond at the surface. And so this matches the extent and height of the Pancake Lake, as well as the lake that the highest extent of the Guru Lake, as well as a lake that was mapped in a different project by my postdoc. So basically, David and Tori worked together and looked at a number of different scenarios, but the two scenarios that sort of fit the most of our lakes were this scenario A, which is a subhumid scenario, so an aridity index of 1.5. And I should say, those of you that are familiar with Alan Howard's work with Yo Matsubaro, it's very similar to their X ratio, or X factor, X ratio, I think, in terms of how this is sort of modeled. And so this fit a majority of our lakes. And then there's also this sort of semi-arid condition, so basically a drier scenario. And this fit, not the remainder, but kind of a number of other ones. And so here I'm just showing this data in a different way. So here, this is the latitude and then elevation, and this is showing the inferred lake level from Tori's mapping, or the black dots. In cases where we have lower lake levels, like in Gale, this is in the triangle, and then the model output for either subhumid or semi-arid, so where we'd predict the water level to be. And what we found was that 11 of our 22 lake levels corresponded to subhumid conditions. And in this particular scenario, 13% of the water would have been from runoff, 26% of the water was from groundwater, and 61% of the water contributing to the lakes would have been from direct precipitation. The other 5 out of 22 lake levels corresponded really well to semi-arid conditions. So in this case, similar portion of the water would have been from runoff, but much more of the water to the lakes will be supplied now from groundwater. So 54% versus 26%, and now less would be being supplied from direct precipitation. And the other lakes that didn't fit within, that didn't sort of match exactly the 1.5 and 3.5, or somewhere sort of in between 1.5 and 3.5. Now, one of the things we had hoped to see was that all of these lakes were all of these lakes or craters were the same age. And so we were trying to get at the timing of this, and like all things with timing on Mars, it's just really, really difficult. So we kind of stole this idea from Sharon Wilson, who basically was looking at a region where she mapped the age of craters that had a lot of gully networks or fluvial activity, some with moderate and some with none, to try and get sort of to figure out sort of when, like at this age, none of these craters that were, this age or younger had any fluvial activity. But it was pretty hard within our region to do that. So you could see sort of all of the craters impacted between about 3.7 and 3.2. And so this might suggest that, lake activity occurred from the late Noachian, possibly into the early Amazonian. But again, it's really hard to constrain the timing of these lake systems through crater counting. So we tried. Okay, so just some key takeaways. I'm sure I talked really fast, and I apologize for that. I just get really excited about Mars things. But some key takeaways are that, when we map these gully network termination elevations, it provided evidence for 18 distinct paleo lakes and 22 sort of lake stands, since some of the lakes had multiple levels. And this really indicates a greater lake density than previously mapped based off of prior indicators. So most of the time when we say or we're looking for past lakes on Mars, we tend to look at, does it have an inlet or outlet valley, or does it have a delta deposit in it? And so, if these gully networks are sort of an indicator of a past lake level, then there's a greater extent of lakes than we previously thought in this region. The majority of lakes identified near Gale, including Guru, correspond to more subhumid conditions, and this is actually wetter than previously interpreted based on the lower post Mount Sharp Gale Lake stands. So this is a wetter climate than we had originally thought for this region. The modeling, and I didn't go into this, we did some calculations just balancing runoff with evaporative losses. So assuming that there wasn't a need for groundwater, indicates that a groundwater component is likely required under both the subhumid and semi-arid conditions. And this is just because if we do sort of the simple mass balance of runoff versus evaporative losses using a range of evaporation rates for early Mars, it requires really high runoff rates that aren't typically predicted in sort of other climate models. So we really do think that groundwater component was really needed to stabilize lake levels, and that groundwater would have sort of been connecting these lakes to each other. And then basically the challenges with crater counting do make it difficult to discern the rates of climate change within the region. And that's timing is such an important thing. It's such a desired thing for Mars science, and crater counting just has a lot of caveats and things to think about. But we suggest, or at least in the paper with Tori, we suggest that there's a general drying trend from subhumid to semi-arid conditions. And this is sort of based on the detailed geomorphic mapping in Gale and Guru. So we see that trend in Gale. And so it makes sense that, it would be reflected potentially in the broader region. Okay, so that's all. Thank you guys so much. And I also want to say, this isn't on the talk, about the talk, but as the EPSP program committee chair, and since this is an EPSP Connects talk, I just want to thank all of you guys for being so awesome with sessions and putting sessions in and helping with putting abstracts in. So I know a lot of you on here participate in all the AGU things. And so I really appreciate that because you guys all make my job so much easier. So just put that out to community. So thank you. And I will stop sharing.
Well, thanks, Marisa, for such a great talk. I'll invite Diane Wagner on to help us field questions here. Yeah, round of applause, absolutely. Thanks for such a comprehensive talk. So the chat is now open for questions. If you have any, I can unmute. It's not a problem. We have enough people here today where that's fine. But while people are typing, I do have a question to start us off. You had mentioned that the Guru crater matches with your subhumid climate condition. Does the persistence of that lake change dramatically depending on the different aridity scenarios?
That's a good question. That's actually something we didn't tie together, in terms of sort of thinking about, it's kind of like we did in terms of thinking about the persistence of the lake, it was more about how long it would take to build this delta feature up. And so that was sort of like a end member way to think about it. But yeah, I'm guessing that, I don't know if they would need to be tied together. The hydrologic model doesn't really have a timing component in it, I guess. It sort of is under these conditions, where would water pond versus sort of if we were able to if we had a better idea of how some variable in climate change, where we could say okay, if we know greenhouse gases are declining at this rate, and we could put it into the model and then say something about, how long the lakes would have persisted for. That's not my wheelhouse, but I definitely think that would be cool for the modelers out there. And that's kind of our hope. A lot of what I do, or my group does, is really trying to put some observational constraints on things so that people who are good at doing sort of the detailed numerical modeling, it's at least these are now they're little wells, and someone can come in and say, okay, what can we add to the model? Can we match these observations?
Great, thanks. Right. Maybe it was so comprehensive we don't have any questions.
Just not good at explaining things.
All right, so our first question is from Johnny Peterson, and it is, could you tell anything about runoff based on the gully networks, discharge or capacity type of things?
Yeah, that's a really good question. We didn't do that, though I've thought a lot about that. I've thought a lot about that actually from a terrestrial perspective. So thinking about gully incision and mechanics at Meteor Crater, And now there's another place in the Arctic that I've started to do work trying to understand sort of the amount of water or ice that's needed to form these gullies. Because right now we can use the equations we use for channels. It's just probably not appropriate because these are steep features and they don't act the same way as like the equations that we use for the channels carving the canyon. We're kind of assuming like this is a normal river channel and we are using our like traditional like hydrologic and sediment transport mechanics that we like know and trust. The gullies are, we could do it. It just probably wouldn't be right, or probably. So I do think it's like an area of, I don't know if it's an area, like people are working on it, but it is something I've been thinking about because that would be awesome, to use those features to get at how much total water would have come in or how much water it would need or ice to sort of snow to carve them. So we're working on it, Johnny, just haven't gone there yet.
All right, our next question is from Noah Benitez Nelson. So if the surface water was a large factor in filling these ancient lakes, has any watershed analysis been conducted to determine the possible movement or origin of this water, i.e. rain, ice cap, etc.?
No, that's a really good question. We did this for, the Peace House fan, which I didn't talk about today, we looked sort of at the morphology and did some analysis and felt like snowmelt was probably the most likely source of water. And that's often what, people will say. And I think part of that is just because of the climate. It's so hard to get an actual warm climate. So most of the time it's thought that the source of water would be that you're getting snow deposition in sort of these alcoves on the crater rim. And then when you have favorable conditions for melting, you're getting melting. And some of that we also did, like Edwin Kite has a really nice model looking at where snow and ice would deposit and then where it would also melt and then estimating runoff rates from that. And so in our calculations, we were comparing sort of our runoff rates to what he predicts with snow, and it lines up pretty well. But I think that's like, obviously that's another thing. That's what that would get at the climate piece that we haven't got at yet, is like, can you do this with like were these lakes ice covered? Because if they were ice covered, that affects that evaporation precipitation ratio a lot. And so then you could have lakes last longer potentially with, because you're not evaporating as much water if there's like an ice layer on top. We don't see evidence for that in Gale that I know of. I know some people are looking for within the sedimentology, like, do we see evidence that the lakes were ice covered and that, sediment can get transported across the lake ice and then it deposits? And like, that's something Don Sumner and Francis Maria Hernandez work on. And so I don't think they've seen any evidence in the sedimentology yet for that, but that's like a really important constraint that it would be nice if we could figure that one out. That would help with the climate question.
We have one more question from Corey Hughes. He says, do you see any evidence for the regional groundwater influence along or beyond the scarp of the hemispheric dichotomy? I have to wonder if the aquifer was influencing these lakes. Did it reach to the southern lowlands?
Yeah, that's a great question. And that's something that like Francis's work, and I've done other work on this, thinking about whether or not there was a northern ocean or whether the small, like there's a lot of deltas along the crustal dichotomy, like scarp, and whether those were filling into also small lake systems or a larger ocean system. Some of the output from these models, so we didn't do, I guess, Corey, like we didn't do like a big enough grid with the numeric model to say like, we didn't go too far into northern lowlands, but under some of the conditions, yes, like there would be, like in that subhuman condition, it would start to fill up the northern lowlands. So then that would indicate sort of, water ponding in potentially like an ocean or like sea environment. So that is also, that's like a project I just got funded, will help like think about that. The extent, I guess, of of water in this area and whether or not it is indicative of an ocean.
Great. Well, that's about time for us here. I'd like to thank you again, Marisa. Give you a virtual round of applause here, and hope you all can join us next month, September 22nd, for another science talk. Thanks so much.
Awesome. Thank you, guys.